What we've been working on so far in Chapter 1 is dealing with limits, the properties of limits, how you work with them, what's legal, what's not legal. There you go. Okay. And what we're going to work on today in Section 1.3 is something called average rate of change. And I will typically abbreviate rate of change as ROC. Okay, we've talked before about it's important in business, in industry, wherever it is that you're going to be drawing a paycheck, to have some idea of the direction that business or industry is headed. To have some idea of, thank you. Everybody have a chance to sign this? Everybody's good? Great. To have some idea of what your client expectations are. Okay. When you go into a store now, expectations are very different than it was back in the early 1800s, isn't it? Okay. Back then, the clerk typically knew everybody who came in. Everybody had an account, and they just kept everything on the books, and people would just come in and plump down money. And there was no such thing as credit cards, right? There was no such things as whipping out your phone and paying for it via your phone and all this kind of stuff. But things have changed. Okay? The way the store looks, the products the store carries, it's all very different than what it was back in the 1800s. If you are not careful, whether you own or work for a business, to be aware of the trends, the client expectations, the available products, what's going to happen to your company? It's going to fail. So you've got to know not only where you are, but where you're headed and where that particular sector is going. The whole point of talking about rates of change is to get some understanding of the direction stuff's headed. For example, let's say you're in a business meeting and your company has fourth quarter results posted on a display when you walk in, and this is in terms of millions of dollars. And this is by year. Now let's say this is something like 2013, 2014, 15, 16, 17, and by this late in the season they know what the 18s are. So these are going to be fourth quarter postings, okay? What the total revenue was. And let's say that this is 50 million. And here's 100 million. Now be careful because this is revenue, not profit. Why is there a difference between what is the difference between revenue and profit? Yeah. Yeah. Revenue is how much comes in, and profits how much do you get to keep. Because it's entirely possible. Casinos, for example, may in a week's time take in $2 million. But in that same week's time, they're probably going to pay out $1.9 million in prizes. Casinos work on a very thin margin. They usually do like 3 to 5% that they keep for themselves, and the other 95 to 97% is paid back to the customers. Why do they pay back at such a high rate? So you keep coming back. And it feels like you're winning. And if it feels like you're winning, you're having fun, you're going to keep coming back. But what they're really after is a large amount of money passing through the casino, and they keep about 5% of it. The bulk of it going back to people in the way of winnings. And what they're after manufacturers have very small percentage. So realize that revenue might be high and profit might be significantly less than what the revenue is. Okay, so that's an example where there's not much margin for profit. Okay. Places like General Electric, they sell jet engines. Oftentimes they sell them to the military at cost or below cost. How can you sell products at below cost? How can GE stay in business and make a decent, healthy profit? Okay, stocks. Well, stocks is money that people's kind of loaning you. Okay, it's kind of actually an interesting market as far as with the jet engines. Okay, on their engines, especially as the military, they'll sell them at or below cost. But the catch with a jet engine is, can you go on eBay and get the parts you need? They can't go to Pratt Whitney or Rolls-Royce and get the parts they need for a GE engine, can they? Where's the only place you can go for GE engine parts? GE. And where they make their money then is on the parts end of the deal. So basically they're putting the engines into the planes for free, assuming that they're going to make their money back on the parts. So there are a lot of companies that people just say, oh yeah, they're just ripping everybody off and blah, blah, blah. And their margins aren't that big. Okay, so you've got to really be good. You've got to really be on the ball because, well, in the case of a casino, their margins depend on, let's say, 4%. Okay, if your revenue changes by 2%, is that a good chunk of change as far as what's going to happen with your revenue? Yeah. Okay, so small changes can really affect things. GE, are those contracts important? Yes, they are. They fight hard to win those contracts. Okay, so let's say we got something where in 2013 revenue was like this, revenue's up here, revenue's up here. Let's say revenue's there, there, and there. I'm just making up some numbers. We'll kind of guesstimate where those numbers actually are here and go with that. We can talk about two different things. One is an average rate of change. What an average rate of change looks like is if you have a function that's shaped like that, we're going to want to get an equation that pretty well fits it. Any suggestions on a model that might fit that data fairly reasonably? Yes, sir. But yeah, the quadratic can work great for that. That'd be a real good choice. It's a simple model. It's not a real high-powered where you get craziness going on out on the ends. Easy enough to work with, but it'll have the same shape basically that we're looking for. With regard to rate of change on something like this, if we were focusing on the first few years here, let's say from 2013 to 2016, you could compute an average rate of change. I'll abbreviate this as ROC. In 2013, let's say that this is 15 million, or 50 million, sorry. And let's say, I'm just kind of guesstimating, let's say it's 90 million. I'm just kind of guessing what that number is. Okay, so we've got 50 million, 90 million in revenue. If you just look at those two pieces of data, sounds like things are doing really good and there's not much to worry about, doesn't it? We almost doubled our revenue. Do you see something of concern, though, in that graph? You're headed back down, aren't you? After about 2015, something happened. Something needs to be addressed because this company is about back to the revenues that they were in 2013. Okay? If you just look at the average revenue between, for example, 2013 and 2016, you play connect the dots, and not the average revenue, but the average rate of change in revenue. And do you see that the slope of that particular line segment is positive? What a positive slope tells you about your rate of change is that the revenue is doing what over that time frame? It's increasing. Does that average pick up the fact that while overall it's increasing, in the last year things have been not good? It misses that completely, doesn't it? If you were to do the average rate of change over that time frame, we could take the 2016 values, and 2016 is the 90 million. We could take the 2013 values, and that's the 50 million. Got to pay attention to what the units are, dollars and years. And remember, this is in terms of millions of dollars, not just 40 bucks. Okay, so this is going to be a total of 40 million per 3 years, which gives you about 13.3 million per year. Those units are important. If I just walked up and said 13.3, that doesn't tell you a whole lot. However, if you're told that the average rate of change in revenue is $13.3 million per year, that's a whole lot to say, isn't it? But that's the way you're going to have to communicate in the business world, not just 13.3. There's a whole lot of stuff that goes around those numbers to give those numbers meaning. What this is saying is that between 2013 and 2016, on average, your revenue changed by how much a year? 13.3, and because it's positive, it was going up about 13.3 each year. Does that make sense? That piece of information is very different from, let's see if we can, let's try something like this. If we looked at just this one point and drew a tangent line, the 2016 slope, if we just did the slope, the tangent line, in 2016, do you see it's negative? Does that make sense to everybody? That paints a very different picture about revenue than this average rate of change from 2013 to 16, doesn't it? You really need to have both pieces of information to have a fuller understanding of what's going on with this business. Overall, we've been making money, but this year, dude, our revenue's dropping. We've got to figure out what's going on. Okay? There are two different ways to look at rate of change. What we've talked about here is average. And then when we turn to just 2016, we've turned to looking at a different type of rate of change. Over a period of years, over a period of time, you have average rate of change. If we're looking at just 2016, that is what is called instantaneous rate of change. An example, the difference between the two is, let's say, headed up to Cleveland for a hockey tournament with Daniel. We jump in, we get there 4 hours later. We've done about 200 miles in 4 hours, so how fast have we been going over that time frame? About 50 miles an hour, haven't we? Now, that 50 miles an hour is the average you looked at for the whole time frame, the whole distance. However, does that mean that at every point along the way to that tournament we were doing exactly 50 miles an hour? Doesn't mean that at all. We might swing into Cracker Barrel. We've never gone to Cracker Barrel in a hockey tournament. It's always cheap stuff. But let's dream big. We stop in at Cracker Barrel and we get lunch. Takes about an hour. That's usually why that money. Okay? Now we've really only been on the road 3 hours to do 200 miles. For the actual 3 hours that we're on the road, now what's the average? Yeah, between 65, 68, something along in there. It's gone up, hasn't it? Oh yeah, we had to pick up gas a couple times. That knocks off a little more time. Still. Yeah, we're 70, a little more than that. Oh man, we had to stop at Pirani's and try on some new hockey gear. 80, 85, okay? Now, if we happen to be doing 85 as we drive past a state trooper and he goes, blink, and he pulls us over, he says, dude, look at this. My speed gun's got you at 85. Yeah, but officer, it's going to take us 4 hours. It's 200 miles. Average, we're only doing about 50 miles an hour. We're okay, right? Because we're averaging 50 miles an hour. You're laughing. What's the problem? No, I keep it down. I figured out it's cheaper and actually faster to not speed and get tickets. Because the 40 minutes you're pulled off to the side costs you 40 minutes of driving. Well, yeah, there is that. And it costs you, I don't know how much, but it costs you on both. But you all get the point. Do you see the difference between the average rate of change speed and instantaneous rate of speed? They can tell you very different things. They can give you very different stories about that trip. They can give you very different stories about the company. Now, here comes the catch. How do you compute the instantaneous rate of speed? Technically, instantaneous is at how many points in time? 1. Okay? That's okay. Yeah, we're going back up to 2, so hold on to that. It's okay. We're going to have to cheat and use 2 and call it 1. But the catch is, even though we're just at 1 point, we need how many for the slope? 2. Yeah, Chuck, we've heard about this before. How do we resolve this? We take the point we're interested in and we pick another point and do what? Slide it closer and closer and closer and closer. And what's that piece of mathematical machinery that lets us take and slide the other one called? A limit. Yeah, calculus. Okay? A limit. The way we're going to do the instantaneous rate of change is by doing a limit. Just making something up here. Let's say that the model for this is 1/4 x squared plus 30. How did I get that equation? Pretend that we plugged the data into the calculator, did the regression analysis, and that equation's what came out. Okay? So let's pretend that's what really happened. Okay? All right. So how are we going to do this then? Actually, this needs to be a negative 1/4, doesn't it? Why a negative 1/4? It's going down. Yeah, way to go. So it should be y equals a negative 1/4 x squared plus 30. If we want to do the instantaneous rate of change, let's say at x equals 16, the reason we could use 16 is, let's say when we plug the numbers in, instead of putting in like 2013 and 2014, we just put in the last 2 digits of the year. It makes the equation a little more manageable. Does it make it wrong if you would have used 2013, 2014, 2015? No. You'll get a different equation, but it'll give you back the same types of results. Okay, so we've got this equation. This equation we want to work with is y equals a negative 1/4 x squared plus 30. I know this doesn't exactly fit it. The problem with this equation is that the vertex is going to be over on the y-axis. It's not slid over. Okay? I'll give you that. Okay, we could tweak it some more and make it like that, but then we get so messed up in the algebra we miss out on what we're really after. Okay, so what are we after here now? We want to know exactly what's going on at one point in time. But the catch is we can't use one point in time because then we don't have 2 points. So what we're going to do here, we want to work at x equals 16. So we're going to do a limit as x approaches 16 of this negative 1/4 x squared plus 30. Okay, so on your calculator, how can you do these limits close to 16? Okay, what we can do here, see if it's still up and running. Ah, there it is. Over to the left side, look at there, a calculator. How about that? What we can do is fire this pupper up. We're going to go to y equals. And in y1, I'm going to do a parentheses, negative 0.25x squared. See, the squared's there. Plus 30. Okay, I guess I didn't really need the parentheses, but there it is. There's my function. You got it in yours okay? Then what I'm going to do is I'm going to check the table setup because who knows what it is on this one. Go to second table setup. And do you see where it says independent? It's on auto. Where do I want it? Yes, sir. It's on my computer. Yeah, I tried to get fancy and that's not working either, huh? Okay. No, you're fine. You're fine. Should I switch over to the calculator and just skip this fanciness stuff? This doesn't want to grow any. The reason I'm doing it this way is because now it's on the movie. So you can see it at home as well. That's why I switched it over. Okay. Okay, yeah. You can watch it again and again and again. Okay. On table setup, independent, that's the x variable. It needs to be on ask. Well, to get it to ask, you move the down arrow until you move it over to where it says ask, and then you press enter. And that will set it up so that it will ask you what x value you want in there. Then if I go to table, so I'll press second and table. Now when it goes to table, remember I want to be close to 16, don't I? So I can put in numbers like 15.9. Equals. Things like 15.99 equals. And it's getting closer to a negative 34. It went from negative 33.2 to negative 33.92. And if you want to see where it's getting even closer, we can do 15.999 equals. And there we are. We're at negative 33.99. Do you buy that it's getting close to negative 34? If that actually reflected what this particular data was doing, if that model was really this data, that would say that at this point the slope would be a negative 34, wouldn't it? What does a negative 34 mean? You're sitting in a business meeting, not a calculus class. They've got that data up on the board, on easel, or they've got it projected on a PowerPoint slide. Okay? Yes, sir?
I got everything plugged in, but it's giving me 9 for a while.
Okay, well, compare it against on the movie or something, we'll figure that out. It may be that the function's plugged in differently. Okay? Check it against on the movie here. What does the negative 34 foretell the company? Okay, you're sitting there in this meeting. Are you concerned? I'd be way concerned. Why? Your revenue is dropping by $34 million this year. That's what it's suggesting is going to happen. That's not good news. Okay? That can't continue long. Your peak was $100 million profit. How many years can you keep this up? Maximum. Like 3 years, right? Because if you do 34 million this year and drop another 34 the next year and drop another 34 the third year, you're down to basically $0, right? You're having a clearance special. Okay. Looking at the average rate of change is one thing. Somebody in the meeting might get up and say, you know, the company's really doing great. Okay, so we got a bad year in 2016. But look at this. On average, we're cranking, man. We're growing at $13.3 million a year in revenues. And you're there, dude. Look at 2016. Talking to the person next to you. Am I missing something here? Or there are two very different ways to interpret this data, aren't there? Based on how you do the measurements. In 2016, it says we're in trouble. And let's say all that we had is up through 2016. Let's say that this other data wasn't even available. Okay, let's just say that that's all we have. I would not be a happy puppy. And that means I would be pointing out as strongly as I could, yeah, well, that's all in the past, but look what's happening here more recently. There's something changed. To get instantaneous changes, we've got to do this limit stuff. What we need to do is we need to move into, algebraically, how do you go about doing these instantaneous rates of change? Notice I said rate of change. If you look at the average rate of change, what was that looking like up there in the upper right corner as the formula goes? Wasn't that looking like a slope? Okay. If we go down and we do the instantaneous rate of change, the way we will figure out the rate of change is basically the same as what we have been doing. Bless you. We're going to give it a slightly different name. We're going to call it a difference quotient. And we're going to work with the idea that along this graph, we've got a point we're interested in, and we have another point that we're going to use as our second point to create a rate of change. This rate of change is going to look like we've got this point x, we've come over some amount h, the coordinates of this point are going to be x, and how do you get the y value? y1. Good. Where's that value y1 come from? From the graph. It's the y value, isn't it? And if you have a function, you plug the x value into the function, and the number that comes out of the function is the y value. So the way that you indicate that you're going to do the y values, you can do this f of x stuff. Does that make sense? For this point, be careful, because we started here at x, we're moving over some additional amount, which is going to put us at a new location. If I start here, 10 feet from the wall, and I go boom, boom, and step over another 5 feet, now how far am I from that wall? 15. I started at 10, moved another 5, flattened up. This new x value is going to be, we started at x and we moved some amount h. Does that make sense? Which then gives us the coordinates of this point are going to be the x plus h. The y value is going to come from plugging the x value into that same model. Okay. We're going to play the game just like we always do. It's a slope. You take one of the points. I'll grab this one. And you plug it in. And I'm intentionally saving a little bit of space in front of this fraction. I'm going to write down a slope, which means I'm going to do the y value over the x value. Does that make sense what I just did? Subtract. Now I'm going to go to the other point. Its y value is f of x, and its x value is x. That's a slope, isn't it? This is also cleverly called a difference quotient. Where's the word difference come from? Yeah, you're subtracting, aren't you? Difference means subtract. And quotient means division. Oh, we're subtracting and dividing. That's really what that title means, isn't it? It sounds big and scary. Difference quotient. We're subtracting and dividing. Oh. And we're going to do one other little thing, and this is what's going to turn it into calculus. Right now, this is just algebra. You ready for calculus? Add a limit. You're on it. We're going to do a limit as h goes to, what value is h going to approach? It's going to get closer and closer to what h is, so the value for h is going to 0. Does that make sense? H is, how big of a step did we take? H is the step size. If we take a step of 0, how far have I moved? None. And we want to stay as close as we can to our original point of interest. On that revenue problem, the point of interest was 16, wasn't it? Okay. Does this make sense so far? Everybody okay? What don't you like? Okay, yeah, where does 0 come from? Look way over to the right-hand side. Over here on the right-hand side, we have the point we're interested in. And what we're going to do is we're going to take this second point, because you need 2 of them. Why do you need 2 of them? Slope. Way to go. We're going to take this second point, and just like the bead on the wire at the doctor's office where kids slide them around, we're going to take that second point and we're going to slide it over closer and closer to the first point. And as you slide it closer and closer and closer, what happens to the value of h? It gets smaller and smaller. This over here, that h approaches 0, is allowing that to get smaller and smaller, so that the second bead is sliding in to be close to the first one. Does that make sense? Okay, now this is what we're going to work with. This is going to drive everything we do slope-wise, derivative-wise for the rest of the year. Not just this semester, but next as well. This is going to run the whole show. Okay, so it's going to run the whole show. How do we use it? How do we use this thing? Well, the way it gets used is, let's start with a simple example. Let's start with something like y equals x squared. Sort of like what our data looked like flipped over. I don't want to get the negatives and stuff in there. I don't want to get too ugly. If we want to know what the slope is on y equals x squared, y equals x squared goes like that. If we want to know what the slope is anywhere along that parabola, is it always going to be the same or is it always changing? It's a different value every place along that parabola, isn't it? Okay, so we need a different value as the values of x change. The way that you get the equation for the slope is you use this difference quotient. It's not a subliminal message to go to Dairy Queen and get ice cream. Okay? We're going to use the difference quotient. Drives my kids nuts. Dad, what are you thinking? To get the equation for the slope, I'm moving it down a line because I'm looking over to the right and thinking there's no room for what we've got to do. I'm going to pull in what the difference quotient is. Well, it's the limit as h goes to 0. Now, let's clean this up a little bit as we copy things down. In the denominator, you have x plus h minus x. What's that simplify to be? H. So in the denominator, we can just put down h. In the numerator, do you see that we have f of x plus h? Time for an infomercial. Okay, let's try something like this. If we had f of cat, what that means to do is find the function named f. Well, let's call this one f. Copy down that function, which is something or other, and you square it. And then what do we put into the function? Cat. So we'd get cat squared. Does that make sense? If we had f of mess, what would that equal? Mess squared. If we had f of x plus h, what's that going to equal? X plus h squared. Does that make sense from the notation? Sometimes people are never really quite comfortable with that notation, and they run into this and, really? Oh, that's what it means. Now I get it. Okay, in this case we square it because what? Because that's our equation. It says you square the x. You square whatever you're plugging in. For this particular function, the first thing it says to do is do f evaluated at x plus h. F means to look up whatever the function is. Well, that's going to be whatever the value is we're interested in squared, because we're using x squared. And what's going to drop inside of there is the x plus h. That's a y value. That is a y value. Does that make sense to everybody? Following along on that top line, the difference quotient, it says minus f. Well, I'm going to copy down what f is. F is something or other squared. F of x says, what are we putting in? X. Equals. One of the things folks will often ask is, do I have to keep using that limit as h goes to 0? And the answer is yes. It's kind of like if you've got a to-do list, things you got to get done this weekend. Okay? I don't know how things work at your house, but at home there's a list on the refrigerator. Clean the gutters. Weed the flower beds. Do this, do that. Or mom's just there after dad. Clean the gutters. Clean the garage. She's got the to-do list stored somewhere, doesn't she? Okay? Does anything ever come off of that to-do list before it's done? Short of just giving up? No, it stays on there till whatever is done, right? Think of that limit as h goes to 0 as the to-do list. That cannot go away until it's done. Well, what does done look like? It means we plug in 0 for h. Can we plug in 0 for h right now? No. You're absolutely right. What would happen if we did? It'd be undefined because we get a 0 in the denominator, wouldn't we? Okay, so let's see what we can work on. Now I'm going to make a mistake here, so don't copy this down. We're going to get x squared plus h squared minus x squared. What did I mess up? X plus h? What about it? Well, I got to cancel the x squareds out, so I'll give me h squared over h, which is h.
No, like you have to FOIL.
Foil? Something's got to be foiled here? What needs to be foiled? This is kind of sneaky. Okay. Something that I see happen very often, every year in fact, is people will take this exponent of 2 and they distribute it. And they get x squared plus h squared. Are you allowed to distribute an exponent like that? No. In fact, what do you really need to do there? You need to FOIL it. This part right here really looks like x plus h, doesn't it? When you FOIL that, you're going to get x times x, x squared. X plus h, xh. X times h, xh. And you got an h times an h, h squared. What really winds up being the case is when you apply the squaring to the x plus h, you get an x squared. But notice you get some other terms. You get an x plus h and an x plus h. So how many of those do you have? 2xh plus h squared. Then, I forget who said it, somebody over here, about dealing with the x squareds. Do the x squareds subtract off? Yeah, they do. But we got to keep this to-do list going because we haven't dealt with h yet. We do have the x squareds canceling. However, in the numerator we have more left than just h squared, don't we? We have 2xh plus h squared. Okay, so we take a look at this. Can we plug in the h yet? Will that work? Nope, because everything's 0. You get 0 over 0, don't you? Well, that's not going to work. That's an indeterminate form. Equals, so we have this limit as h goes to 0. We can factor out an h. We're going to have 2x plus h over h. Is everybody good with that? Now what do we do? You can cancel an h, can't you? Does everybody see that? That at this point, an h in the numerator will cancel with the 1 in the denominator. And what that gives us now, man, do we still have to drag along this limit as h goes to 0? Yep, we've not actually done that work yet. We get this function, 2x plus h. Is it okay to plug 0 in for h there? Yeah. And if we plug 0 in for h, what are you left with? 2x. Now, notice I plugged in the 0 for h, didn't I? Is the to-do list done? Yeah, I plugged in 0 for h, and look what happened. The limit went away, didn't it? That's when you're allowed to drop the limit. Is as soon as you plug in 0 for h, you can drop the limit. If you do it before that, that's a problem. Okay? And I know sometimes some folks think I'm getting a little crabby about it. I'll take off a point or two on a quiz or a test because they dropped the limit 3 or 4 lines up. I do that because when you get to main campus and elsewhere, if you drop that limit early, somebody's going to blow a gasket. And they're going to say, where'd you learn to do this stuff? Well, Chuck made us carry the limit. You do too, huh? Okay. So I don't want you going elsewhere thinking you can just drop that whenever you want to. You can't drop it till it's actually done. Let's go after another one. Hey, what's this good for? 2x. We've got it. What is 2x anyway? Well, it's the answer to whatever the question was. Oh, what was the question? What is the equation of the slope? Okay, well, the equation is 2x, isn't it? If, and I'm going over to the right side of the screen, if we want the slope over here at x equals a negative 3, what's the slope at x equals a negative 3? Negative 6. You plug the negative 3 into that function that we got down here. You plug negative 3 in for x, and what that tells you now is the slope at this point is negative 6. If we want the slope over here at positive 1, we would take the 1, plug it into this same function, and what's the slope over there? 2. The point of computing these slopes isn't to just be able to say, well, I know what the slope is. Do you? The point is to figure out how something's changing. By using this limit as h goes to 0, you're figuring out how something is changing at one specific point in time. Like when you drive past the state trooper. Not the whole trip to Cleveland. Okay? Does that make sense? Let's do another one of these, just to be careful. I'm going to go a little faster. Let's say that we're modeling some data, and the equation turns out to be f of x is x squared minus 2x plus 5. You ready? Real fair question. Get the equation that will estimate the slope anywhere on this function. Get the equation that will estimate the slope anywhere on this function. So what we're doing now is we're computing a slope, aren't we? When we do, this limit as h goes to 0 of this f of x plus h minus the f of x over h. Hey, is this starting to become familiar? Like, geez, Chuck, is it? Will it just go away? No, it won't. Rats. Equals. Well, we're going to keep up this limit as h goes to 0. I know what's in the denominator. It's going to be h. The first part of the numerator says, look up this function, and what are we going to put into the function? Yes, ma'am.
Oh, I actually have a question.
Oh, yeah.
From the original equation, do you not have to do on the denominator the x plus h?
It subtracts off.
So you don't have to even put that on there?
Right. You can if you want to, but here in the upper left corner, see where you have x plus h minus x. It simplifies to just give you an h, and every time it will. So that we can take a shortcut on. Okay, so what are we going to do with this? It says to copy down the function. Well, it's something or other squared minus 2 times something or other plus 5. Everybody good with that? What goes into the something or other? X plus h. In both locations. Minus, then it says copy down the function, minus 2 times something or other, plus 5. And this time what goes into each of the something or others? X. Equals, the limit as h goes to 0. Have you ever written down a problem where one step is this long before? Good. So you're toughened up, ready to go. Now what we're going to do is first square the x plus h. So that gives us x squared, 2xh, h squared. Then we're going to distribute this negative 2. So we're going to get a minus 2x minus 2h plus 5. There's the first portion of that numerator. Everybody good? Minus. Then we're going to have an x squared minus 2x plus 5 equals the limit as h goes to 0. We can do a little bit of canceling here. Notice it's a minus. So we're going to have x squared minus x squared. Is everybody good with that? Here we have a minus 2x. Here we have minus a minus 2x. Those will cancel. And the last thing they'll cancel is the plus 5s. That leaves us then with 2xh plus h squared minus 2h all over h. Everybody good? Next move. What's next? Factor out an h. So we're going to have h times 2x plus h minus 2 over h, and the h's will cancel. And the good news is that this next step, we have this limit as h goes to 0. We're going to have 2x plus h minus 2. Is it legal to plug in the 0? Yeah. So we can drop the limit, and what we're going to get is 2x minus 2. This allows you to compute the slope anywhere on that function. Does that make sense? Being able to survive the algebra to compute these equations for slope is real important. Folks, I'll see you Friday. I hope you have a good day.